Hi guys, so in this video we're going to look at decoders. We're going to look at 2-line to 4-line and 3-line to 8-line for both gated and ungated. So I want to be able to confidently draw the logic diagram for all of these, draw the truth table for all of these. We can confidently approach any decoder circuit question, fully confident of what we're doing and what's going on. Alright, so recall the definition of decoders first of all. A decoder is a logic circuit that's able to take n inputs and convert it to a maximum of 2 raised to power n output lines. We covered the reason for this in the last video because we need to be able to know which particular state is triggering which particular inputs. So the first decoder we're going to look at is the 2-line to 4-line. So it's meaning that looking at our inputs, we have D1 and D0. So these are 2 inputs, n is 2. Okay, so let's see. Given that n is equal to 2, then our number of output lines, m, is going to be at most 2 raised to power 2, which is 4. So this is a maximum 2-line to 4-line decoder. We have y0, y1, y2, and y3. All right. So let's look at how we can make sense of this. We're going to be able to have to draw the function table for our decoder 2, by the way. All right. So we have 2 major inputs, D1 and D0. And it's important to note to carry out a handful of checks before you start solving. The first thing you can see that this is ungated. All right. So you can say ungated. We know that the purpose of a gate or an enable signal is to activate our circuits. All right. So which means that with a gate or an enable signal, can I call it enable or a gate? Even though I toggle D1 and D0, I can toggle them. As long as my gate is low, all right, none of these will affect my outputs. So this is an ungated decoder, all right? So meaning I can, if I would like to fill my function table, I can write D1 and D0, okay? Then fill this in as I would a regular truth table, right? 1 0 1 1. Okay, so we can now look at our outputs. D1 is being drawn to the negation. So do we have D1 here? Okay, D1. This is going to be not D1. Okay, so this is D1 all the way through to the end. Okay, not D1. And same goes for D0. This is D0 at this junction. All right, so at this line we have D0. And here we're able to bring it to the becomes D1, not D1 after the negation. Okay, so that's not D1 after the negation. So although usually you're used to seeing inverters with the bubble after the circuits, it really doesn't affect much if just a single bubble is drawn before the inversion. All right, it's one and the same thing. Sometimes it's done so that you don't confuse the bubble for a junction. Okay, so let's look at this. If we were to fill this normally, we can look at y. Let's try and fill y0 first. Y0 is an AND gate connected to not D1, so we can follow it to not D1 and not D2. So let's make this explicit, and not D0. Okay, meaning that the things entering my y0 are not D0. The inputs to my y0 and y0 AND gate are not D0 and not D1. Okay, so these are my inputs to my y0 gate, meaning that for the case where D1 and D0 are both 0, my y0 is going to be high. So I'm also able to tell that this is high because the circuits used for my decoders are the AND gates. Okay, I recommend you watch the previous video where we explained the difference between active high and active low logic. So since I'm using AND gates, I'm using active high logic, which means that when my inputs are triggered for the AND gates, I'm going to have a binary 1, and my circuit is going to be normally low or normally 0. So since these are where my inputs are connected to, every other situation is going to be a low. All right, so that's D1, not D1 being 0, and D0 being 1 is not connected to my AND gate at all. So I can fill the rest as a 0. We perform the same operation when handling Y1, okay? We can see that this junction is connected to not D1. So for us to help ourselves, we can write not D1 here. And that this is connected to, you have to follow it all the way up to D0. So for the case where not D1 means 0, okay? And D1 means 1. Same thing. D0 is 1, not D0 is 0. Okay? So perform the AND of 0 and 1. So not D1 is 0, D0 is 1. I can see that my output is going to be high, since those are the particular cases for my Y1 inputs. So I can go ahead and write this high and fill the rest of my circuit as 0. Okay? Do the same as handling Y2 and Y3. Y2 is all the way to D1. Okay? And second junction is all the way to not D0. Alright? So that's 1 and 0. 1 and 0. So that means D1 is a 1. D0 is a 0. That's this case. I'm going to write this as a high and fill other cases as low. Same goes for my Y3. I'm going to look at it. And this goes to D1. So that's D1. Even has a space here. D1. And this goes all the way to D0. So if you're asked to draw circuits, draw certain decoders, this is the same logic you're going to use. We're going to have to be careful to indicate very carefully with these big junction circles, so you're able to tell without mistake where your output line is drawing its inputs from, okay? So this is 1, 1. So that's my Y3 is going to be high for the case where this is 1 and 0. So everything else is filled as low. So that's all we have to do when handling decoders, all right? So this is a 2-line to 4-line decoder. And next up, we're going to look at the 2-line to 4-line gated decoder. Okay, this is very similar to the circuit we just handled before, right? But looking at it now, we can see that we've introduced a G. This is a gate. This is our gate signal. If you recall when we introduced in the former videos why we need an enable when handling flip-flops, all right? We can see that it's able to tell us when can my circuit be active, all right? So looking at this, these are AND gates. So this is an important thing to note. So AND gates mean I'm dealing with active high logic. Okay, so let's fill this in. I'm going to have G for my gates somewhere over here. Then D1 and D0. I'm going to fill my gates as 0 first. So not G, 0. 1 actually. Okay. Then we do only 0, 2 zeros for these cases. I'll explain why later. Then we fill in D1 and D0 as we would do so normally. Alright. So 0, 0, 0, 1, 1, 0, 1, 1. And then we can repeat this all over again since we're changing the gate signal from 1 to 0. 0, 0, and let's say 0, 1. We have 4 output lines, Y0, Y1, Y2, and Y3. Okay? Is our function table or our output table. Alright. So looking at this, what happens with our gate? Our gate signal. Okay. So our gate signal, as we remembered, is our enable. So when our gate signal is high, then it means that all the other aspects of our circuits can come on. Cool. So looking at this, this means that if our gate is 0, if our gate signal is low, then nothing in our circuits is going to be able to function. But since we're dealing with not G, and not G is being inverted, so that means you're going to have the complement of not G, which is the same as G, meaning that for your gate circuits to be high, that means throughout this line your gate circuit is high. So anywhere this guy is high, my output is going to be activated. Because for a 3 input AND gates, okay, if I have a 3 input AND gates, let's say if these first 2 are data and the last one is my gate, right? So like this were my gates. As long as this is low and both of these are 1, my output is always going to be 0. so far as I'm dealing with an AND gate. But once my gate signal becomes 1, then my output is activated and I'm allowed to continue. All right. So granted that my gate signal is 1, anywhere else that my gate signal is not 1, I'm going to write as an X. So this X stands for don't care. All right. It's inhibited. It's not a permitted state. It's not allowed. It's not covered in the domain of this 2 line to 4 line gated decoder. So we can get one as we normally would. All right. So for Y0, consider it's connected to gate G. That's cool. It's following not D1. Okay, so we can write, so this is not D1. And it's also hooked up to not D0. All right. So that means this is going to be 0. So we have not, why not? Is equal to not D1, not D0. Okay. Which is equivalent to 0, 0. So that's the case we have here. I'm going to fill this as a 1. Remember that we're filling this as a 1 because since we have AND as our primary logic gate for this decoder, then we're dealing with an active high configuration. Active high configuration means my circuit needs to be high, my output needs to be high to indicate that a state has been chosen, meaning that I am normally low. Okay? If me being high is to stand out, that means every other state is regularly low. So we did the same for Y1. Okay? We're hooked up to our gates as usual. Then at this point we have, following carefully, not D1 because this is the inverter. So not D1. And over here we have straight up D0. Okay? So Y1 is not D1, D0, which is the equivalent to 0, 1. We can fill that in as high first, zeros for the rest. Y2 hooked up to my gates. Now this is changing to D1. And this is becoming not D0. Okay? So Y2 is not, is it D1, not D0, which is equivalent to 1, 0. The case we have here. We fill this particular case as high for Y2, 0, 0, last one as 0. And then for Y3, my gates to be enabled. And then this is to D1 without inversion. This is to D0 without inversion. Okay? So that's D1, D0. It's the same as 1, 1, which is the case we have here. Okay? So filling up decoders is a pretty fun process. Remember, you just have to be careful. Am I dealing with a gated decoder or not? The first thing I have to check. Check the state of your inputs, and then more importantly, check the primary gates being used. An AND gate will tell you there's an active high configuration, and an AND gate will inform you that you're dealing with active low. All right, then lastly, to have a really nice time when dealing with it. Okay, so lastly, before we go, we deal with a 3-line to 8-line gated decoder, which looks really complex, but is actually pretty fun to do. Remember the steps we said we have to take. The primary gate for this circuit is a NAND gate. Okay? So what does the NAND gate mean? The NAND gate means I'm dealing with an active low logic. Active low logic means that to indicate an output, to indicate a certain state, my output is low. For low to count, that means my circuit is normally high. All right, so we see how that plays, how this is different from the other circuits we've covered in this video. We have a gated inputs, so we're going to start with our gates G. Okay. Our inputs D, C, D1, and D0. Okay. So the trick in the slide before this, I used G and I indicated that my output was allowed to be on if my gate was high. That is a 1, right? But if when writing my truth table, I put not G on this table, right? So gate being 1 means that the not gate is 0. Okay, these mean the same thing equivalently, right? So if I'm using not gate here, that means that my circuit should be active for every situation where my NOT gate, the NOT value of my gated input is going to be 0, okay? Let's fill that in. 1, 2, 3, 4, 1, 2, 3, 4. And then let's leave one situation where our gates are not, the NOT of our gate input is high. Alright? So we'll fill this in as we would do normally for any binary. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. Okay, and then we can fill this in with any regular inputs. Remember what we said, that our gate allows us to have an input. Okay, so let's quickly write out not y0, not y1, not y2, not y3, 5, 6, 7. All right. So the first thing we're going to do is that we're going to make every case where our gate is low to be a don't care situation. All right. That is not covered in this decoder. If my gate is not allowed, then nothing can be allowed to change my output. All right. That's the first thing we handle. So you make the exact same process as we've done before. My four input AND gate. My gated signal is here. Then for y0, this is figured up to D2. So this is not D2. Okay. This is not D1. And this is not D0. Okay. Meaning that for y0 is going to be 1, 1, 0, 0, 0. Alright. So that's 0, 0, 0 for my gates. But it's important to know that I'm dealing with a NAND circuit. That's active low. So y1 is going to be not y0. It's actually going to be 1, 1, 1. So for this situation, I'm going to write my circuit as 0 and fill everything as 1, since this is normally high. Okay. So that's what we have to do when filling this up. We can continue in the same vein for not y1. So this is on not D2. Okay. This is on not following the junction. This is on not D1. And this is on D0. Okay, so that's going to be this. And fill everything as normally 1. Alright, so you can go on like that continually and so on and so forth. But you come to realize that it follows a very nice diagonal pattern down. You can check this yourself. Okay, 1, 2, 3, 4. As you go on. To fill in the rest of the. Alright. So we can see that our truth table is mostly populated by 1s, which is what happens when you deal with active low configuration. Like I said, normally active low configuration, which means normally high. Alright. Which means that for my signal to happen, I have to pull down my output from a 1 to a 0 to continue. For dealing with active low, I have to pull up to 1 to indicate that this has been activated. Alright, so we've been able to cover decoders in this video. In the next lecture, we'll look at 7-segment displays and how decoders help us to create numbers and hexadecimal symbols. So I'll see you in the next